So we've looked at simple pole methods. Now what happens if you have a multiple pole? Well, there is a formula which always works. It's a rather complicated formula, and if you can avoid using it, then I would avoid using it. We'll see there's other approaches to finding the residues in multiple poles. But anyway, I'll explain what the formula means. So the important thing is that this value m is greater or equal to n, where n is the order of the pole. And the question is, well, how do you choose m? Well, your first instinct is you don't want to differentiate this thing that many times, so you want to make m as small as possible. So normally you would choose m to equal n, but there are instances, depending on what phi is, where you might actually end up choosing m to be larger than n, as we'll actually see in this example here. Okay, I think I won't bother going into the proof of where this comes from. We'll just go straight to I've explained how to prove it here. I'll let you work that out for yourselves. Right, so let's actually see how it works. So in this example, we want to find the residue of sine z divided by z minus pi cubed. Now, the first thing to realize is, well, what type of pole do we have here? Well, it's pole of order 2, because we've got a when z equals pi, sine z is 0, obviously. So we've got a simple 0 divided by, and when z equals pi, this is obviously a 0 of order 3. So a simple 0 divided by 0 of order 3 gives us a pole of order 2. So it's pole of order 2. But if we're going to apply this formula here, then you can see z naught is where our singularity is at pi. So if we just had m equals 2, then we'd have to differentiate, phi is sine over z minus z pi. We'd have to differentiate sine divided by z minus pi, which is not not such an easy thing to differentiate. It's actually much easier to differentiate if we have m equals 3, which would then cancel out the z minus pi. So there are instances now and again where we actually choose m to be larger than the order of the pole n. So to make it life easy for ourselves, we choose m equals 3 in this case in the formula. Then we have to differentiate twice. The thing we differentiate, fortunately, is easy. It's just sine z. So we can differentiate sine z twice, which gives us minus sine, and we need to evaluate it at the singularity. So in this particular case, if you evaluate sine z at z equals pi, we get the answer. We get the answer 0. So in this particular case, the residue is 0. There is another way of doing this, and that is if we let as delta equals z minus pi, which is the normal thing to do if we're using the sort of Laurent series method. Then this is actually also easy to show, because then if delta equals z minus pi, that means z is equal to delta plus pi, which is z of sine of delta plus pi is just minus sine delta. Okay, add pi to any argument and it just reverses the sign, and we're dividing by delta cubed. So this is then very easy to see what's happening. Taylor expansion of sine delta gives you delta minus delta cubed over 3 factorial, etc. And then we divide by delta cubed, and you see that there's no 1 over delta term. So that means the residue is 0. Right, so which method should we use? Do we use... we've actually already done another multiple pole method, which is the Laurent series. That's the one we did first. So this Laurent series method works for any type of pole. So that's an alternative for an alternative multiple pole method. My suggestion is that if your pole is located at 0, or if m is greater than 2, I think this m should possibly have been an n. I think I meant the order of the pole is greater than 2. Finding the Laurent series is usually the faster method for finding the residue. No, I think I'll stick with m here. Yeah, so if you have to differentiate too many times, it's too much effort really, unless of course it's something simple like sine. So as it was in this case here, for example that example we've just done. Now we come on to a third method. If phi is a derivative with respect to a parameter of a function phi, whose residue is known or easy to find, then we can use this following result. I think what I'll do here is just skip to an example and then go back to see exactly what's been happening. So if I want to find the residue of z squared minus a squared to the minus 2, so I 1 over z squared minus a squared squared at z equals a. Okay, obviously this is a double pole. So I could use this multiple pole formula, but I think there's an easier way, and that is to actually first find the result for the simple pole. So rather than having to the minus 2, we just look at what the result is for the simple pole. So for the simple pole, 1 minus z squared minus a squared, obviously it's got poles at z equals plus a and minus a. But okay, we're after the simple pole at z equals a. And the residue of that is easy to find. It's a simple pole. So we just use the p over q method. So p is 1, q is, sorry, p over q dash method. P is 1, q is z squared. So z dash, q is z squared. So q dashed is 2z. So we just end up with 1 over 2z, and z equals a, so we just end up with 1 over 2a. Very quick. Now, this is the clever thing. What we can do is differentiate both sides with respect to a. Okay, so if we differentiate, when I say both sides, we actually differentiate the function we're trying to find the residue of and the answer. Okay, so we differentiate this thing in here with respect to a, with respect to the parameter a. So if I differentiate with respect to a, what do I get? Well, I get this thing squared, and a function of a function, I got minus 2a on top. So, well, I get a minus 2a from the a squared minus a squared, and I've also got 1 divided by, so I get a minus factor of minus 1. So I get 2a divided by this thing squared. Okay, this is just the differential of this with respect to a. Okay, and then I differentiate this with respect to a as well. So I end up with this. So then all I do, this is a linear function, so I can take this 2a outside and then put it underneath. So I end up with the result, the residue of the thing I'm trying to find, the residue of 1 over z squared minus a squared squared is just minus 1 over 2a squared divided by 2a, which is minus 1 over 4a cubed. Okay, so it's quite a neat method. So going back to what the formula is. So what we've just done is we use this result here, that if you know the residue of some function phi, which has a parameter a, you can differentiate that residue, and that will be the same as if you take your function of phi and then differentiate with a first and then ask what the residue is. Okay, so probably you can understand it better from the example. Okay, but here's the formula you can use. Again, I think I won't bother going through the proof. It's there if you want to study it.